for joining us for another Trane Engineers Newsletter Live program. I'm Jeannie Harshaw, and today we'll be providing an understanding of demand charges and time of use rates and how they impact the financial payback of various energy saving strategies. We'll start by providing an overview of the electric energy market. Then we'll break down the various charges in a utility bill and how those charges are calculated. And finally, we'll discuss operational and equipment strategies and various energy resources that can help your building respond quickly to the changing energy market. Today we have Evan Berger from the Trane Energy Solutions Group, Paul Valenta, Vice President of Sales and Marketing, and Justin Weeman from the Trane Applications Engineering team to cover this topic. So Paul, can you get us started with an overview of the changes happening in the energy market?
Sure, Jeannie. Understanding what is causing the electric utility industry to change so quickly is a vital background to understanding the technology, behavior changes, and facility designs that can help overcome these inevitable utility changes. This knowledge will help facility managers and building owners do so transparently to help keep operating costs as low as possible while maintaining comfort, productivity, and reliability. The utility changes we'll review are essentially helping to modernize the largest mechanical system in the world, the electricity grid. The grid was designed and configured decades ago and optimized for growth, knowing the source fuels that created the electricity provided the ability to dispatch as demand required. Monopolies were essentially created to generate, transmit, and distribute electricity with legislated returns and reliability goals. That model was and is a traditional customer-vendor relationship. When Congress approved the amendments to the Clean Air Act of 1970, it was the beginning of real change to clean up the air and reduce emissions to slow climate change. Upgrading the legacy electric grid design to fit today's criteria is too expensive and not realistic, so generation, transmission, consumption, billing, and information transfer are all changing for the cleaner grid. The relationship between producer, distributor, and customer is morphing into more of a partnership, all working together in order to have clean, resilient, affordable electricity. Defining the pollutants allowed the sources of those pollutants to be categorized into groups, which is shown in this graph, national emissions by source. Stationary combustion is in blue, industrial and other processes are shown in orange, highway vehicles in green, and non-road mobile is shown in purple. These groups produce, as a part of their process, carbon monoxide, ammonia, nitrogen oxides or NOx, particulate matter, sulfur dioxide or SOx, and volatile organic compounds or VOCs. For example, the main source of SO2 or SOx comes from the blue category, stationary fuel combustion. In fact, the blue category is shown in each emission category. This is the source grouping where electric utilities are placed. So electricity generation has been a key contributor to dirty air, so changes are occurring in the utility to meet legislative requirements. As this EPA chart of declining emissions shows, the United States has made great progress since 1990, reducing emissions. These amendments set the stage for protecting the ozone layer, reducing acid rain and toxic pollutants, and improving air quality and visibility. As our population and economy grows, EPA measurements show dramatic reductions in pollutants. Carbon monoxide is down by 65%, sulfur dioxide by 88%, and VOCs by 40%. The progress of declining emissions, as dictated by the 1990 Clean Air Act amendments, did not come without cost to different sectors of the economy. Pollution controls on automobiles, construction equipment, and of course electric power plants proved to be expensive and market changing. So what are some of the challenges facing the utility industry resulting from the Clean Air Act? First, an aging infrastructure in both generation and distribution. These assets need to be updated or replaced. The graph in the upper left shows 46 coal plant retirements from 2009 to 2015 alone. Capital is required to replace and/or update those assets. The graph in the upper right shows that much of the replacement generation is coming from cleaner, non-dispatchable, low-utilization generation, which requires capital to maintain load matching, flexibility, and reliability. The path to more capital is more energy sales, but the graph on the lower left shows that energy or kilowatt-hour sales remains flat, which puts pressure on income needed for reinvestment. The graph on the lower right estimates the capital requirements in the electricity markets, growing to over $300 billion with a B by 2025. To meet regulations, electricity generation is changing. A Bloomberg study in 2015 illustrates the downward trend of fossil fuel generation with that of clean energy generation. Coal fuels are certainly in decline and won't be seen in a growth curve anytime soon in the industrialized world. Natural gas is cheap and a lot cleaner than coal, so there's some new construction or updates of natural gas generation. And of course, solar and wind generation, forms of renewable energy, are growing too. Keep in mind, while we continue the discussion, the difference between fossil fuel generation and renewable generation. Fossil fuels can be thought of as stored energy, dispatchable energy, or energy storage. How can this dispatchability or grid flexibility be put back into the grid with renewable generation? If the sun doesn't shine, how can the solar panel generate electricity? Knowing the challenges facing utilities and grid operators, it's important to understand how the grid started, how it worked, and where it will go. Why? Because these changes will change how electricity is priced, which directly affects the electricity market and how users will consume electricity and manage load. Later in the program, Evan will discuss how electricity is billed, and Justin will discuss operational and equipment strategies to help keep costs low. The old grid was designed for quick growth, maximum reliability, and minimal cost with fossil fuels as the basic fuel. One company, the local utility, typically owned all of the assets, generation, transmission, and distribution, and energy flowed from the generator to the user one way. As the nation grew and demand increased, the utility would petition the Public Utility Commission and get approvals and permits to build new generation and transmission assets to serve customers' needs. Lowering emissions and aging infrastructure has caused electric energy stakeholders to change how they think about the grid and how the grid should be designed and operated. Going forward, the modern grid will look and operate in a very different manner, as you can see. A smart grid is where groups of interconnected loads or customers and distributed energy resources, or DERs, become a controllable smart microgrid. Justin will speak about different types of DERs and the advantage they provide later in the program. Energy and information flows in different directions, not just one way. Building owners can connect or disconnect from the grid as needed, enabling the buildings to operate in a grid-connected or island mode. Load information is shared with the grid so operators can maintain reliability and reserve. This smart grid is connected to the main grid. In this microgrid scenario, the grid increasingly becomes a source of backup power should the microgrid be capacity short. When looking at this, I ask myself, what has to happen to my facility to participate in this microgrid? Simply consuming electricity might not provide enough operational flexibility to mitigate high demand cost periods. This new grid will require some building energy agility, different building design processes as well. With lower emissions and improved efficiency in mind, architects and engineers are changing the way buildings are designed and built. Net zero designs are becoming more popular to lower energy intensity as well. There are many definitions of net zero. Some include all forms of energy and some go back to the source energy. Here the building has some renewable generation available and access to the grid as well. Urban buildings don't always have space for a lot of renewable capacity. Building designs are more efficient. Locations are closer to users, main highways, bus routes, and bike paths. For our discussion, basically the building produces as much electricity on-site as it needs in a calendar year. Efficiency is king in net zero designs, using advanced shading, daylighting, low emissivity windows, and heavily insulated building envelopes make the building super efficient so that on-site generation can be a greater percentage of peak consumption. The higher the concentration of on-site generation to peak demand allows excess capacity to be sold back to the utility when building electricity needs are low. When building electricity demands are high, the utility provides the necessary electricity to keep the building operating smoothly. At the end of a calendar year, the net exchange of energy between the building and the utility or grid, by definition, should be zero. If a net zero building were to be truly off-grid, investment in backup sources of on-site energy would be needed beyond solar panels and wind turbines to provide energy when the wind doesn't blow and the sun doesn't shine. Fossil fuel generation, electric, and thermal batteries might be needed to keep an off-grid building operating due to the intermittency of renewable energy. Most net zero building owners don't want to invest in those distributed energy resource assets, so the utility, in effect, is the backup and ends up providing those investment-heavy resources. The utility must be available to provide electricity even though, by definition, at the end of the year, sales of kilowatt hours are zero. Net zero designs stress utilities by reducing load factor even further. Electrical load factor is defined as a measure of the utilization rate of a building or generational asset. It's the ratio of the average load over a given period to the maximum load occurring in that period. If a utility is serving a grid with a low load factor, the utilization of the investment is low, and so revenues cannot be maximized. Think of a load factor in the airline industry with a 100-seat airplane taking off with only 20 passengers. 80 seats left the airport without a paying passenger. The load factor is low at 20%. If only 20 passengers want this destination at this departure time, a smaller 25-seat plane could do the job. Which size of aircraft is more sustainable business model choice for the airport, the airline, and passengers? 20% load factor or an 80% load factor? The aircraft with a higher load factor is the better business choice for all stakeholders. The required investment of a smaller airplane keeps costs and ticket prices low. The smaller airplane means the airport can dedicate less space to optimize its other space for other airlines, destinations, departures, and passengers. A high load factor utility customer is the same as a full plane of passengers. It has high utilization. Utility customers with short duration peak loads have a lower load factor, like the big airplane taking off with many empty seats. There are more costs to serve low load factor customers, so ticket prices or electricity prices will be very high. Utilities can keep costs low by partnering and serving customers with predictable loads and higher load factors. Utilities and grid operators can encourage customers to have high load factors with rate and rebate incentives to install systems that can help manage demand. This ISO New England hourly load duration curve is for 2005 and 2006. ISO New England is the grid operator in the Northeast. The average grid demand for 2005 was about 15,000 megawatts, while the peak demand was just under 27,000 megawatts. That's a load factor of just over 50%. Said another way, the grid has twice as many generating assets as it uses on average. A low load factor requires excess capital and maintenance, just like the aircraft example, to build it and keep it operating. A little further inspection of the graph shows that the top 6,000 megawatts of demand, which represents 21% of the peak, was only used for 165 hours. 7 days per week times 24 hours per day is 168 hours. So 21% of the total generating assets were used less than 1 week per year. This graph illustrates a week of demand and pricing from the same grid operator, ISO New England, in late July and early August. On the y-axis is megawatts of demand. Time and day are shown on the x-axis beginning on Monday, July 31st, 2006. The electric load on the grid, the orange line with black dots, is increasing each day until the peak on Wednesday. Thursday's demand is less than Wednesday, and then the peak load gradually gets lower. The peak demand each day occurs just before 4 p.m. and is due mainly to HVAC loads. If 21% of these peak loads could be shifted for a week, the utility's load factor could be greatly improved. Capital requirements would be less, and that means lower prices for everyone. The pink curve shows the wholesale prices spiking on Tuesday and Wednesday, confirming high electricity prices during high demand times tends to be expensive in the real-time or wholesale markets. Low load factors, as we have shown, increase the cost to serve customers. Improvement in equipment, operational efficiencies in buildings have kept kilowatt-hour sales flat, and utility commissions don't like to approve rate increases. Instead, demand charges are increasing. Summer demand charges have increased since 2008 all over the country to help generate revenue utilities need for investment. Southern California Edison has demand charges during peak times in excess of $40 per kilowatt, as does Con Ed, for examples. As stated previously, over $300 billion in investment will be needed to upgrade our grid. Demand charges provide revenue to the providers to purchase and keep up generation and transmission assets and keep them working. New investments mean higher demand charges. This shows a partial list of utilities in the U.S. with demand charges in the $14 per kilowatt range and above. As a result of the changing electricity marketplace, let's review what our electricity consumers are facing to help provide some guidance or hints at designs and operational changes and partnership opportunities within your facilities moving forward. Rising demand charges, that's how the utilities can earn income to offset investment because energy sales, that is sales of kilowatt hours, remains flat. Consumers are changing to LED lighting, using solar energy, and improving efficiency. Customers in some regions with heavy solar are also facing utilities that are implementing new demand charges called facility charges or coincident demand charges. Legacy demand charges are charged when your building peaks. Facility demand charges is another demand fee charged for a building's peak contribution to the grid peak. If the peak building demand occurs during the utility peak, the two demand charges coincide and are additive. As more solar comes online, the grid peak may occur later in the day, which may be at a different time than when the building demand peaks. In either case, it's a new charge, and managing demand becomes very important to save money. Customers are also facing tougher efficiency in building codes and implementing their own sustainability and financial goals. Keep these points in mind as you listen to Evan and Justin in the remainder of our program, and think about how you can implement new operating processes, designs, and asset investment so buildings can operate in the changing grid efficiently and affordably. Building energy agility provides the ability to move energy in and out of a facility or generate it nearby during periods of excess generation or high demand. Energy agility provides the building operator with choices to purchase electricity on peak or off peak. Building energy awareness is understanding the economics of using different energy sources and building resources to supply a building's thermal and electrical requirements. The important takeaway is that not only is it important to manage how much energy is being used, it's important to measure and manage when and where the energy is being used. It becomes apparent that operating a building sustainably and efficiently is not enough to reach sustainability and financial goals. Planning for the interdependence of interconnected loads, energy suppliers, utility systems, and information will be a necessary process moving forward. Consumers and utilities can partner in some fashion to invest in on-site distributed energy resources while updating internal infrastructure to help reduce costs and support sustainability goals. Technology today, thank goodness, will allow consumers, utilities, and grid operators to behave more like partners, each doing their part to keep air clean, costs low, efficiency and reliability high. Have you investigated installing more robust M&V for optimized management? Does the local utility have an incentive-based demand response program? Can thermal and electrical energy storage enhancements be included in normal building upgrades or in new construction? Does the utility provide prescriptive or custom rebates for energy storage? Should investments be made in renewable energy, either on-site or through procurement programs? With these systems in place, there are choices, and building operators will ask, what are the costs associated with using different energy sources? What component of my building is using most of the energy and when? How can I reduce consumption? How can I match building demand with purchases? Can I demonstrate my facility's load factor to suppliers to get a better rate? Planning a path to energy agility and energy awareness is very important in the new grid, and now is the time to start. Evan Berger is going to take over, walking you through step by step the different parts of an electric bill to make sure everyone understands how electricity is being charged by your utilities and grid operators so that costs can be managed and long-term plans made and implemented to optimize electricity cost savings. Evan?
Thank you, Paul. When it comes to explaining electric rates to customers, I like to start with conclusions first and work my way backwards from there. The first thing I usually say is that when it comes to reducing your electric bill, there are three and only three ways to do it. First, you can buy fewer units of energy. That is to say, you can take on energy conservation measures. This is something you folks in the audience already know a good deal about, so I'll leave ECMs for another day. Second, you can purchase electricity when it's cheaper, at night. There are a number of reasons why electricity is cheaper in the nighttime off-peak hours than it is in the middle of the day. Most of them relate to the fact that demand on the grid is lower and that these lower costs are passed on to consumers. This is mainly what we'll discuss in this section. Finally, in deregulated states, specifically much of the Northeast and in Ohio, Illinois, and Texas, most large customers buy their electricity from a third-party power supplier. For folks in these regions, you can leverage a higher load factor, as Paul discussed a few minutes ago with the airplane analogy, to negotiate a better rate with your supplier. The second conclusion that I share with customers is that the electric bill you get at home is very different than the bill that your firm's CFO gets on his or her desk every month. At home, almost all of our electric bills are based on usage, which is the amount of kWh you consume over the course of the month. For commercial, industrial, and institutional customers, utility costs are based partly on usage, but an equally important and far less understood part is the demand portion of the bill, which is something I will cover in great detail in just a little bit. The last conclusion is that all this stuff, electricity rates, the tariffs that underlie them, is quite a bit complicated. If you don't have an accounting degree, it can be daunting to decipher a monthly utility bill, and it's even harder to read through the regulatory filings. And unfortunately, many of the utility account reps that I've worked with over the years don't really understand all of the factors at play. So we're going to try to help make some sense of all this in the next few minutes here. Let's start by discussing demand charges, which I mentioned before. Put simply, Demand charges are any line items on the bill that are assessed in dollars per kW. Utility demand charges are based typically on the highest 15 or 30-minute interval of power consumption over the course of the month. This is why I often liken demand charges to the speedometer of a car. Think about it this way. The odometer tells you how many miles you've driven, or, in a building's case, how many kWh you've consumed over the total period. The kW is more like the speed gauge. It tells you how fast you've been moving, or how many kW you consumed when your building was using power at its highest speed. There are two types of demand. The first is utility demand charges from our local providers. Many customers are less aware of grid demand charges. Grid operators, such as PJM in the Mid-Atlantic, ERCOT in Texas, and others also have a demand charge as well. This is oftentimes known as the capacity or ICAP charge. It can be very expensive. In the Canadian province of Ontario, for example, the global adjustment charges from their grid operator, called IESO, cost 50% or more of customers' total annual utility expense. That's a lot. So be sure to keep in mind these costs as well. Why do these demand charges exist? To understand that, you need to know a little bit about our modern electric system. I want to bring back a slide that Paul showed us before and give it a little more context. Here is a very, very simple diagram of the modern electric grid. It's broken up into three parts: generation, transmission, and distribution. Generation is the fleet of power plants, coal, natural gas, nuclear, hydro, wind, and solar, that provide the electricity. They burn fuel, or they harvest sun, wind, and water flow to produce kWh, which they then send through the transmission system. The way that most generators get paid is by selling their electricity in terms of cents per kWh. They need to recoup the cost of fuel and also make a profit. Transmission is a system of power lines that take electricity from the generators and move it vast distances at high voltages. The distribution sector is what we commonly call utilities. This is the network of poles and wires that takes high voltage electricity off the grid, steps it down to lower voltages, and then delivers it to end users like homes, schools, and offices. Our transmission and distribution infrastructure is sized to meet the max load that the grid has as a whole, and also the max load each neighborhood and each individual requires. There's no tolerance for blackouts, so transmission and distribution owners must build to accommodate the worst-case scenario, which we call the peak, and must operate and maintain that equipment to 100% reliability. It's peak demand, not the total kWh consumption, that grid operators and utilities are concerned about. And this is why they charge customers in terms of that peak max demand. To really illustrate how demand charges work, let's take a look at an actual utility bill. I was able to get permission to cut and paste this bill because it's been addressed to my employer. It's a winter 2018 bill for one of the Trane buildings in La Crosse, Wisconsin. The total bill is just a bit over $20,000, and the building itself consumed 204,000 kWh over the course of the month. That might lead some people to do the simple math, divide that consumption by the total cost, and conclude that the electricity costs 10 cents per kWh. But that's not the whole story. Let's walk through this bill line by line to get a better sense of the picture. After the customer charge, which is a hefty $180 per month, we see the on-peak and off-peak energy charges. On-peak charges, which in this case are 9 a.m. to 9 p.m. weekdays, are 7.5 cents per kWh. Off-peak rates on nights and weekends are about 35% cheaper at 4.9 cents per kWh. Altogether, the usage charges come to about $12,500. Skipping a line, we come to the two demand charges. The first is the customer demand, which is $1.50 per kW. The second demand charge is called on-peak winter demand, and that comes in at $10.78 per kW. Altogether, these two demand charges cost nearly $6,700, or about 36% of the total pre-tax bill for the month. Let's blow up the demand charge line items and have a closer look. As you can see here, not only are the dollar values different, the kW values are different as well. The on-peak demand sits at only 476 kW, but the customer demand is more than double that at 1,036 kW. What's that all about? This is called a ratchet, and to understand demand ratchets, we need to take a look at the utility tariff. Here are a few paragraphs that we've cut and pasted from the Excel Wisconsin tariff. Generally speaking, tariffs can be hard to understand, but if you know where to look, they can be helpful. Here we see two definitions for demand charges. The first is for on-peak demand, and the second is for the, quote, distribution demand, which on the bill itself is termed the customer demand. As an aside, it's not uncommon for terminology in the tariff to differ from the names of line items on the bill, like in this case here. These tariffs can be frustrating, but don't just throw your hands up in despair. There's a lot of value if you can figure these terms out. So, for the on-peak demand, we can see that the charge is based on the greatest 15-minute load within that one billing month. The distribution, or customer demand, is quite a bit different. It is the greatest 15-minute period not just of this month, but at any time within the past 12 months. This is what we call a ratchet. The highest peak is ratcheted up and carried through for an entire year. In this case, our office bill example hit its peak in the heat of the previous summer when it was blasting its air conditioning full throttle. But that charge carries through on the bill at that elevated number even during the wintertime when the AC is off and the building is being conditioned with natural gas heating. Ratchets are very common in utility rates. I would say that over half of the nation's utilities in all regions of the country have them, and they're impactful. In this case, the ratchet adds 660 kW to the customer demand line item, and at $1.50 per kW, it costs this customer nearly $1,000 here in this 1 month alone. So, when you're designing air conditioning systems, even in colder climates like La Crosse, Wisconsin, you need to be mindful of those ratchet costs that can come even when the AC system will be idle all winter. So we've learned a bit about demand charges, but how do they impact day versus night pricing? Well, we know what the on-peak versus off-peak kWh rates are. So if you take that roughly $12 per kW demand charge and blend it into the day rate, what you find is that kWh costs 14.9 cents during the day versus just 4.9 cents at night. This means that energy is 60% cheaper at night. Or thinking about it another way, roughly 3 times more expensive during the day. Think about it this way. When we're out driving, we're always scouring around for the best gas prices. It might be $2.49 a gallon at one spot, but $2.35 a few blocks down. For electricity, our power can be 2/3 less expensive at night in that off-peak window. If you had a chance to head out after dark and buy some gas for 75 cents a gallon, when would you fill up? That's an audacious claim, so let me back it up. We know that this office building is going to hit its peak during the on-peak window and will be unoccupied during nights and weekends. So right off the bat, we can be sure that the demand is a daytime phenomenon. So let's take that $12.25 demand charge and blend it in. To illustrate this, we'll use round numbers. Let's look at a hypothetical building with a 1,000-ton peak load and a water-cooled centrifugal chiller system. At peak, when it's running its air conditioning at full load, this 1,000-ton unit, at an efficiency of 0.8 kW per ton, including the pumps and cooling tower, the chiller plant would add 800 kW to the summer kW demand. At $12.25 per kW, this would add $9,800 to the monthly cost. That $9,800 is the numerator. Remember, we are trying to go from dollars to cents per kWh. So the denominator is the number of kWh that chiller plant consumes over the course of the month. It's a 1,000-ton unit operating, let's say, at 10 hours a day at a 75% diversity factor, multiplied by its efficiency, the 0.8 kW per ton, times 22 weekdays a month. That equals 132,000 kWh. When we take the $9,800 and divide it by the 132,000 kWh, we get an approximate demand cost of 7.4 cents per kWh. So the daytime energy is the 7.5 cent rate plus the 7.4 cent demand adder, or 14.9 cents in total. That's 3 times what you pay at night. At night, it's just the 4.9 cent energy, and the demand is essentially zero. So we've covered a lot here, but the takeaway is this. Don't just assume a flat rate. Don't take the total bill divide it by the total kWh, and call it a day. That can be very misleading. To really understand the true cost of daytime power, you need to consider the demand charges that almost all commercial and institutional customers pay. Let's illustrate just how big a role demand can play by looking at an example project. This right here is a hypothetical example for a school in Louisville, Kentucky. Truly, these numbers are 100% made up. I created them myself. There are a lot of numbers here on this slide, and you can just ignore them. The only one we care about is the one at the bottom. If you take this customer's annual spend and divide it by the total kWh for the year, you'd come up with 10.4 cents. Our example is going to show just how misleading that number truly is. So, our hypothetical K-12 customer has a 25-year-old, 200-ton air-cooled screw chiller that's at the end of its life and needs to be replaced. They ask us for two options. One, a standard chiller whose efficiency just meets the code, and two, a much higher efficiency unit. The school would like to get more efficient, but they're capital constrained, so they've asked us to compare the savings and the paybacks. Let's do it the wrong way first, using the simplified blended rate. If we use the blended 10.4 cents per kWh, you can see that we do get some savings from the high efficiency chiller here. Again, using nice round numbers to make our math easier, let's expect the unit to run at 1,000 equivalent full load hours in this example. And so the high efficiency chiller would save 40,000 kWh and about $4,100 in this simplified analysis. Given that we're looking at a $25,000 cost adder for the high efficiency option, going with the more efficient chiller would yield a simple payback of 6.0 years. It's not terrible. Maybe the school district would bite here and make the efficient choice. But we've learned about demand charges, and so we know better. Let's take a look at Louisville Gas and Electric's tariff for large customers. As you can see here, the actual kWh rate is really low at about 4 cents per kWh. It's the demand charges, the cost of transmitting and distributing the power to the school, that are actually the big driver in utility costs. In this case, the three demand charges add up to $19.89 per peak kW. So, now let's take a look at the more detailed rate, separating out the $19.89 demand and the 4.0 cent energy. The table here shows the cost comparison. Assuming the same 1,000 equivalent full load hours and 6 months of demand shift, we see that in reality, 2/3 of the total chiller's operating cost comes from that $19 demand charge. We get $4,700 in demand savings alone with the high efficiency option, plus another $1,600 from kWh savings. In total, we're saving over $6,300 a year in utility expense for the school. This is 53% more than we would have thought using that blended rate. So now the high efficiency chiller, which had a decent but marginal payback before, now has a much more attractive payback of 3.9 years. The school district is a whole lot more likely to want that high efficient machine now. Well, that's it for this section. I hope you learned a bit, and if you have any questions, reach out to your trusted advisors for more details. With that, I'll turn it over to Justin.
We talked about how the electricity marketplace and grid is changing and how to read a utility bill to understand how you are being charged for electricity. Now let's take a few moments to review some distributed energy resources that can help bring energy agility and awareness to your operation so you can meet your financial and sustainability goals. Distributed energy resources, or DERs, are electricity producing resources or controllable loads that are directly connected to a local distribution system or connected to a host facility within the local distribution system. DERs can include solar panels, combined heat and power plants, electricity storage, small natural gas fueled generators, electric vehicles and controllable loads such as HVAC systems and electric water heaters. These resources are typically smaller in scale than the traditional generation facilities. Distributed energy resources come in many shapes and sizes and tend to be located closer to the loads than typical fossil fuel generators. Some of these assets can be in front of the meter, while others will be behind the meter or on the customer side. The great feature of DERs is their ability to be aggregated and dispatched. For example, the grid might have excess solar capacity during the noon hour. That excess could be dispatched to be stored in flywheels and electric or thermal batteries. And interestingly, wind turbines generate most of their power at night with higher wind speeds. That excess energy capacity from wind could be dispatched to charging assets as well. Conversely, if solar production is low, thermal storage or flywheels could then be dispatched to provide more energy into the grid. The important feature of DERs is to provide dispatch capabilities affordably and reliably. Now, hospitals might find an opportunity in a cogeneration plant to participate, in an office building by use of thermal batteries, electromechanical batteries, and a fuel cell or a curtailment program. It's important to think about the daily duration of assets along with how you are being charged for electricity and what programs the utility or legislative body is encouraging. As mentioned, DERs can be in front of the meter or behind the meter on the customer site. We will take a closer look at these assets starting in front of the meter on the grid side. There are 4 common assets utilized on the grid side of the meter, and they are pumped hydro, batteries, compressed air, and flywheels. With the exception of batteries, these technologies are mainly utilized on the grid side due to the economics of scale. With pumped hydro, the excess energy that is generated powers a pump. That pumps water to a higher elevation, such as a reservoir in a mountain. When there's a need for energy generation, the water is then released down the mountain through turbines to create electricity. Batteries are pretty straightforward. The excess energy produced simply charges the batteries, and their power is then released when there is a demand. Both pumped hydro and battery storage systems have been utilized for some time and are a mature and proven technology. Flywheel is a newer technology that was developed to increase the efficiency of the storage system. The flywheel has the highest efficiency of all the DERs. However, it is the most expensive and it is a new technology. The flywheel powers a motor that spins a rotor very quickly and creating a vacuum. This turns the electricity into kinetic energy. When the grid needs energy, the rotor releases and converts the kinetic energy to electricity. Now, compressed air is the newest technology that's being tested now. It works by taking the excess energy and powering a large compressor. The compressor pumps the air into a depleted gas reservoir, and then the air is released through turbines to generate power when needed. The most commonly used storage technology at the grid level is pumped hydro. And here is an example of a pumped hydro station. This is known as the Bath County Pumped Storage Station. The station has the capability to produce 3,000 megawatts of power, and it's considered the world's largest battery. It consists of 2 reservoirs of water. During periods of high electric demand, water is released from the upper reservoir. That water flows down to the lower reservoir through a series of turbines that generate the electricity. During times of low demand, they use the electricity from the power plants to pump the water from the lower reservoir back to the upper reservoir. And during times of generation, there is over 13 million gallons per minute of water flowing. While this facility consumes more energy than it generates, it allows the other power plants to operate more fully loaded so they are closer to their peak efficiency. Now, here's a table that summarizes the performance and cost considerations of each storage type. Pumped hydro is commonly used due to its maturity, longevity, and the low cost of capital. Battery technology is advancing, and the use of lithium-ion batteries for energy storage is growing both on the grid side and the building side of the meter. Flywheels have a very high installed cost, causing the utilization to be low. Compressed air shows promise due to the low cost per stored kWh. However, it still has low usage due to the maturity of the technology. We are now going to talk about the storage offerings that are commonly used on the building side of the meter. These will be the distributed energy resources that can be utilized on a customer site to create an agile building and manage the rising utility charges. There are two general categories for energy storage utilized at the building level, and those are electric and thermal. Within each of these categories, there are various types of storage technologies available, but only a few are utilized at the building level due to size and cost constraints. For electrical energy storage, it's common to install batteries in the customer's facility. Battery energy storage systems store energy generated from solar, wind, or the electric grid at a time of excess generation, and provide that energy to a business at a time of demand in order to shift load or for peak shaving in their facility. Let's look at thermal energy storage. Many customers these days have financial and sustainability goals to reduce carbon footprint, greenhouse gas emissions, and create net zero facilities. In order to achieve those goals, there is an increasing amount of on-site renewable power generation. Oftentimes, the power is generated at a time the building does not have a demand for it. New research reported in an ASHRAE research paper, RP 1607, shows that thermal energy storage increases the utilization of renewable energy by as much as 50%. Let's take a look at some of the thermal storage technologies available. Thermal energy storage comes in different sizes, shapes, and temperatures. Thermal loads can be stored in the form of ice, chilled water, or even hot water. Similar to a battery system, thermal storage systems utilize the excess energy generated from solar or wind, or at a time when the cost of energy from the electric grid is low. The energy powers a chiller or a boiler to generate thermal energy that is then stored in ice tanks or large water reservoirs when the thermal loads on that building are low. That energy is then released at a later time when the thermal loads in the building increase. When it comes to energy storage, you should always try to store the energy in the same form that it will be consumed, since that is the most efficient and cost-effective method. Store all of your electrical loads in an electromechanical battery system, and store all the thermal loads in a thermal battery system. Based on the economics, it does not make sense to satisfy the building thermal loads with an electromechanical battery. This is a graph representing the levelized cost of storage. It compares the lifetime cost of chemical batteries to the lifetime cost of thermal energy storage with regards to the cost to store 1 megawatt hour. The costs for batteries are the average range obtained from the levelized cost of storage version 3.0. The cost for thermal storage is the conservative case that includes the cost of the storage and the chilling equipment obtained from Ingersoll Rand. From the graphs, you can see that thermal energy storage is around a third of the cost of a chemical battery system. This is one reason why you should store thermal loads in a thermal battery and electrical loads in an electromechanical battery. Now let's look at an example of electrical and thermal loads within a building. Here is the energy distribution for a typical 500-ton building. It is showing the energy contribution from the various loads over a 24-hour period. The bottom four loads, the base, lighting, fans, and pumps, are all the electrical loads. The remaining chiller portion is considered a thermal load. From the distribution, you can see that the thermal loads make up around 30% of the total building's peak load. By adding thermal storage, you can run the chillers at night when the electrical load is low and charge the storage tanks. That stored thermal energy can then be deployed during the daytime during the peak loads to reduce the peak demand. In this example, the demand was reduced by 300 kilowatt and the customer's load factor has increased significantly. As Paul mentioned earlier, a high load factor is desirable to the utility providers and may allow the customer to negotiate better utility rates for their business. A further demand reduction can occur by utilizing an electrical mechanical battery storage system in conjunction with the thermal storage. Utilizing both a thermal and an electromechanical battery storage system in a building provides many benefits and operational flexibility. The conversation should not be about which type of storage system to utilize. It should be about how much of each type of storage should be used. If you zoom in closely to a building's electric load profile, you'll see that the load is jagged. Batteries help with this unevenness because they can charge and recharge throughout the cooling cycle. This jagged characteristic also creates a smaller diversity factor, which is the actual ton hours divided by the total potential ton hours. This results in fewer batteries being required for kilowatt reduction. When the load spikes, the battery discharges. And as the load drops, the battery charges. For example, instead of 6 batteries staying in discharge during the cooling cycle, 3 batteries can take turn charging and discharging during the same cycle. Whereas ice storage is typically used for much longer durations and will not ramp up and down as quickly as batteries. So in a building, it makes sense to first deal with shifting the massive cooling load. Reduce that 20 to 40% of the peak load with thermal storage. Then smooth out the jaggedness of the reduced peak load with batteries. In this way, batteries work synergistically with ice as a complete energy storage solution. Now here are some advantages to consider for both the thermal and electromechanical battery storage systems. Thermal storage is a proven, low-cost technology that is 100% recyclable and is easily recycled. Thermal storage can also be used for demand response over long durations. Batteries, they can power anything, and they take up less space per unit energy than thermal storage. And since they can power anything, they are an excellent resource for backup power. And here are some benefits of utilizing distributed energy resources of any kind for both the owner and the utility company. DERs provide an owner with flex fuel option so they can choose how to provide thermal or electromechanical loads at a time of high demand when the utility costs are expensive. They allow an owner to increase their load factor and negotiate better rates with the utility companies. DERs also create a smaller carbon footprint for facilities and offer resiliency by removing the need for grid power generation. The utility companies also see a great benefit by efficiently utilizing renewable resources and reducing on-peak demand during peak periods. Jeannie, why don't you share the recent case study on how distributed energy resources help both the customer and the utility provider?
Sure, Justin. To close up today's program, let's walk through a quick example of how using DERs can help save money. This building in Houston had a thermal battery system installed in 1993. The size of the thermal storage system in battery terms was just under 1 megawatt. The building had changed ownership a few times, and electric deregulation made it appear that the value of this thermal battery asset was no longer viable. The third-party electricity supplier had portrayed the electricity contract to be a flat rate, and so using the tanks would cost the owner more money. Upon further review of the energy charges, like Evan just reviewed with us, the rate was not flat. It was determined that the lower energy costs could be realized by operation of the thermal battery system. Savings for 2017 were measured at $134,000. Documenting the operation and working with the utility owner, we negotiated a 2-cent rate reduction for 2018, which equates to $200,000 in savings by using the thermal battery distributed energy resource. Peak demand was lowered from 2,196 kilowatts to 1,696 kilowatts during the summer peak. Hopefully today we gave you enough information to understand your local utility charges and designed for the changing energy market to take advantage of potential cost savings. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. And feel free to subscribe to the Trane Engineers newsletter. For those of you seeking continuing education credit, be sure to check out our continuing education programs, which include many past E&Ls, all free and on demand. And remember to fill out a survey and let us know what you thought of today's program. AIA members, please remember to turn in your member information to your local site coordinator. And finally, ask your local host about details for next year's Engineers Newsletter lineup. Thanks for your time today. We look forward to seeing you next time.